Hello, in this video I'm going to discuss how lock-in amplifiers work and why we use them. So let's start with that first thing. Why do we use lock-in amplifiers? Let's say that we have a resistor that we want to measure as a function of time. So it's going to have some variations in resistance. So that's a symbol for a variable resistor. How would I do that? Well, one way to do it would be to take a battery and then run the battery voltage across a larger resistor, so that might be called a bias resistor, and put that to ground, and then measure this voltage right here with your digital multimeter or something else. This is called a DC measurement because I'm applying a DC current right here that's going to go first through this resistor and then down through the variable resistor. And I'm interested in the resistance here, the second one, as a function of time, say. And I'm going to be reading out a voltage that's a function of time. And so if I graph that, in this case, then let's say that, in fact, the resistor I'm interested in is not changing in time. So it's actually got a fixed resistance. The voltage that I measure will hopefully be centered on that true voltage I expect. But due to drifts or fluctuations in the current that's applied, maybe due to fluctuations in this resistance or the battery, or just the measurement noise associated with my meter, the value that I'm going to read out is going to fluctuate around this true value, okay? Or the value of R that I calculate will fluctuate around the true value. And the spectrum of that, if I actually take the Fourier transform of that, and then take the power spectrum, then if I look in frequency space, the power spectrum, or power spectral density, as a function of frequency, will in general, out at high frequencies, will look like white noise if things are working well. So there's just a certain noise level associated with the Gaussian random noise. But the drifts and things like that will tend to have what's called a 1 over F component. So it will be red, in other words, long frequency components, sorry about all that zooming, long frequency components or long wavelength components, low frequency components will tend to have higher amplitudes. And that's a general property of measurements, measurement equipment and noise, that in the ideal world we wish that this was flat all the way down to zero frequency or very low frequencies, but in fact usually there's a 1 over F component that makes your measurement drift. So that seems like a bad thing. So if I want to measure this resistance over long periods of time, I'm going to be subject to this noise. Well, if I could figure out a way to instead move my measurement of that resistance up to these frequencies up here where the noise is white, then maybe I could do this without suffering the effects of this 1 over F resistance. So how can I do that? Well, one way I can do that is by taking this oops, I've got to figure out how to do the erasing thing here, is to take this source that was a battery, and instead I'm going to turn that into an oscillating source. So now I've got an AC voltage that gets applied to this resistance, and I'm really interested now in, let's say this is happening at frequency F. This V of t that comes out is going to be some amplitude times sine 2 pi f of t, and I'm really interested in this amplitude. But now the thing that I'm interested in is the amplitude of a sine wave out at some frequency, which is to say that I'm interested in, if this is f out here, I'm interested in the amplitude out here, which is out where the noise is white. So I can actually use this technique to move my measurement up to high frequency where the noise is white, where I'm not subject to these drifts, and life gets a lot better. The measurements get a lot more stable, a lot less 1 over F, less drifty. So that's what we want to do, and one way of doing that would be to just watch it on an oscilloscope and try and do this, but lock-in amplifiers are a way of doing it that actually have a lot of advantages. And so a lock-in is a way that does this, a machine or a technique that does this in a very clever way, exploiting a few facts that are to go over here. So the facts that get exploited here are that if I have a signal that is oscillating at some frequency, omega, 2 pi f, right, is omega, and I'm going to label that as omega 1, And if I take that and I multiply it by the same sine wave, omega 1 of t, okay? And then if I integrate this over a long time, okay, over time, and I integrate it over an infinite amount of time, and I multiply it by 2, then we know that this integral is equal to 1, or the integral would be a half if I move the 2 to the other side. That's if I integrate it over infinite time, okay? I'm sorry, there's a factor here I need to apply. I have to divide by the amount of time, okay? So that's a property of the sine waves. The reason for that is that if you have a sine wave that's going like this, and then you square it, right? If you square it, then what happens is you get a wave that's sort of going like this, and you notice it's got a DC level to it, right? And the average of that DC level over long periods of time is a half, okay? But obviously if I integrate over long periods of time, I'm just summing a half again and again and again and again, and I need to, to divide by the amount of time that I had to return this average. Okay, so that's the fact number 1 that Lockins exploit, right? Another one is that the integral of sine of omega 1t times cosine of omega 1t, if I do this over an integral number of periods or a long time, okay, so integrate over a long time, that equals 0. Those are orthogonal functions, right? And another one that is exploited is that if I do this, sine omega 1t sine of omega 2t, right, dt, then if I integrate over a long enough time, and we'll get back to what that means, then that also is equal to 0. In other words, sine and cosine are orthogonal if I go over an integral number of periods or over a long enough time, and different frequencies are also orthogonal if I go over a long enough time. And what is long enough depends on the frequency separation right here. But if I have the same phase and the same frequency, then I get this nice factor of 1 here. Okay, so how does a lock-in amplifier exploit these? The lock-in amplifier says, okay, I've got a signal S that is equal to some amplitude, which is what I'm interested in measuring, times sine of omega 1t. Okay? And I've got a reference, R, that is equal to I'm just going to call it 1 times sine of omega 1t. Okay? And what I do is I have some electronics that takes these two things, the signal and the reference, okay? And these lines are going to come in here. Now the signal, first of all, the very first thing that I actually may do is actually multiply this by some gain that I know. So maybe that's a factor of 10, maybe it's a factor of 1,000 or something like this, right? But now I've got A times G times sine of omega 1t right here, okay? I've got a reference here that I can adjust the phase of the reference, and we'll get back to that soon. So I'm going to call this phase adjust, okay? But let's not worry about that yet. And then these things feed in to a multiplier. And I'm going to multiply these two things, and what comes out is S times R, okay? And then I'm going to run that through an averager, okay? And in this case, the averager is going to be something with a time constant, and so we'll just write this as some tau, like this. And then there's finally the output, or I'll just call it out, okay? So that's what the electronic box is actually going to do. It's going to multiply the signal by some gain, and then it's going to multiply that signal times the reference to get to this point right here. This is sometimes called the mixer, and this is the mixer output. And then it's going to take an average over some time scale, which we'll call the time constant tau. Right? So let's look at what things look like here. Now, I drew what sine and sine look like, and then we can bump up the amplitude of this to get it up in the volt scale, rather than maybe this is a microvolt right here, and there's not much signal there. But if I multiply it by 1,000, it's a millivolt, or by a million, it's a volt. And then I can multiply it by these things. And then, of course, sine squared gets that nice DC average there, where I've got this signal that looks kind of like this, where this is 0 volts, and this is actually G times A, right here. Okay, and this output right here in a traditional analog lock-in amplifier now applies an RC time constant, and the RC time constant sort of makes it look sort of like this. Okay, so the discharge time of the RC filter lets this sag a little bit until the next peak comes up. But that's what's happening here. Okay. All right. So in this version that I was talking about before, if I have the integral of S times R dt, right, and I divide by 1 over t, that this would return, well, you would think that it would return the amplitude of S times that gain factor, right? And then maybe if I multiply the 2 here. And of course, the instrument, the lock-in amplifier, knows what gain was put in here, so it can divide that out in terms of the ultimate answer it's going to give back, right? So in the ultimate answer it gives back, it will just, of course, tell you the amplitude on the dial for the output of the lock-in. So you don't really have to worry about that G in terms of what you're reading out on the output of the lock-in. Now there is a little bit of a thing you need to know here, which is that most lock-in amplifiers actually give you an output that is actually the RMS of the waveform rather than its amplitude. That's just a traditional thing. So the most lock-ins will actually give you the RMS of the waveform rather than the amplitude of that sine wave. So really it'd be this over square root of 2. Okay. So a couple of things that are important to know here when you're using a real lock-in, one of which is that you have knobs that actually set this gain factor right here. You have a knob or a dial that will set this phase adjustment right here, and that's important. And you have a knob or a dial that sets this time constant right here. So these are the 3 things that you need to know how to control when you sit down in front of an actual lock-in and start playing with it. This knob right here, the gain factor, okay, is one that if you knew the amplitude of your signal, you would just set it such that with a thing called the sensitivity on the lock-in. On the front panel, most lock-ins call this gain G, the sensitivity. And the sensitivity tells you what level of signals you're kind of expecting. And if you set the lock-in to 100 microvolt sensitivity, that means that if the signal is below 100 microvolts, the G will bring it up to less than the maximum the electronics can handle at this point right here. But if you have a signal that's bigger than 100 microvolts, this amplitude of the signal right here is going to get so big that it's going to rail amplifiers and the voltages will get too big inside the lock-in for it to handle linearly. And a light will come on which will say overload. And so if the red overload light comes on, that just means that you have set the sensitivity too low or this gain too high, and you need to back off on it. So you have to watch out for the red overload light when you're hooking up your signals and tuning up your lock-in. Okay, that's that one right there. The time constant right here is the thing that sets how much this output will sag before the next peak comes along. If you have a wave coming in that has a period, I'm just going to pick a period here, of 1 second, okay? Let's say that was the period of the sine wave there. Well, because this is sine squared, that's like sine 2 theta, this is now the 1 second. So this piece right here is only a half a second. You don't want this to sag away very fast here. In other words, you want a time constant that is long compared to a half second. So if we're setting the time constant, we need to know what frequency that we're going to be looking for. What is this omega 1? If it's a kilohertz, then you need a time constant that's long compared to, say, a millisecond. But 30 milliseconds might be fine, or 300 milliseconds might be fine. That's one bound. In other words, if you're doing a 1 kilohertz measurement, you do not want to set the time constant to be 1 millisecond. That'd be ridiculous. On the other hand, if you set the time constant too long, and then you change something in your experiment, so you change that resistance, then the output here can't respond much faster than this time constant. So if you're just playing around in the lab and looking at dials and that kind of stuff, then you want it to be able to change something in your experiment and have this output change on a time scale that doesn't bother you too much. If you set the time constant to 30 seconds, you're going to need to wait several multiples of 30 seconds before this output will stabilize. So it'll be one DC level, the output will, and then you change it, it's going to slowly creep up to the new value. And if that takes several minutes, you're going to get annoyed. So generally, unless I really had to, I wouldn't set the time constant longer than 1 second because I don't like to wait longer than a few seconds to get to a new value. Okay, so that's the time constant knob that you're going to need to set. The other one you have to set is the phase adjust. Now, remember that if we have a signal here that's going to go into our lock-in, often we have a function generator that is generating the signal that's going to drive our circuit. Okay, and then we're going to take this out and send this to the lock-in input. Okay, and this same oscillator will take off just this place over here, or what's called a sync line from it, that is the same phase and frequency. And we'll send this to the reference, it's called. Okay, the reference, that's the thing we're going to multiply eventually by S. And if our experiment actually has, say, a capacitor in it somewhere, okay, so I'm going to stick a capacitor in here, then there will, in general, be a phase shift that the signal gets, right, S, gets relative to the reference R. So when I send these things over to the lock-in, it's not like one is going to be sine omega t and the other one's going to be sine omega t and everything's going to work out. Instead, I'm going to have the reference is equal to 1 times sine of omega 1t, and I'm going to have the signal is phase shifted somehow, and it could be forward or advanced or delayed, whatever. I don't care, but it's going to have amplitude, and then it's going to be sine. I'm going to call it omega 1 t plus phi s. Okay? And we need these. You remember that sine times sine gives you this nice thing over here, but sine times cosine, which is to say if this gets rotated 90 degrees, sine times cosine gives me 0, right? So what I really want to do is I want to have a way to add in a phase shift to the reference. So I will call that phi sub r, right? And that's the purpose of this box right here, which is another knob on the lock-in. You get to adjust the reference phase, okay? This is just what it is according to your instrument, okay? But what you want to do is you want to adjust this to match the signal phase. And this is, so you'll find a place on your lock-in where you can actually adjust the phase, and that's the phase you're adjusting, and you can adjust it to maximize this output right here to get the 1 out of that integral instead of the 0. Okay. All right, so there is a need as the thing coming out, oops, excuse me, to that, which is that one way to adjust that phase is actually, since you have S equals A times sine of omega 1t plus phi s, right? If you adjust the reference phase, I'm sorry, that's not A, that's 1 times sine of omega 1t plus, I'm sorry, I'm blowing it here for a second, plus phi r, right? If you adjust this so that this is kind of like the sine, and this is 90 degrees out of phase with it, right? So this is like the cosine, which is to say, if phi r is equal to phi s plus 90 degrees, then you get 0 output, right? Then you get the out equals 0 case because you have sine and cosine being averaged, multiplied and then averaged, right? And this turns out to be the most sensitive way to actually set your phase. If you tune your output phase such that you get 0, if you just go into the right number of degrees such that you get no output, and then you hit a button on the lock-in that suddenly says, okay, phi r, I'm going to change it to the current phi r, so the phi r prime is equal to the current phi r plus 90 degrees, right? Then that actually brings you again to the beautiful maximum where these two phases are the same, okay? And it's more sensitive, a more sensitive way of setting the phase adjustment is to first go and make it so one is sine and the other is cosine, which is to say get 90 degrees out of phase, zero the signal, then hit the button that says switch it by 90 degrees, please, and that'll give you the maximum. Okay. All right. So going back to thinking about doing this measurement and thinking about Fourier transforms, what I now have is a signal that is at some frequency. Okay, this is the time axis. It's got noise on it still, right? And that noise, if the power spectrum of the noise, if I took the Fourier transform of that, took the power spectral density, right, of this signal with the sine wave on top of it, remember the noise has the white noise and the 1 over f. And the signal now I've put out here, so there's actually a line now in my power spectral density due to the signal, right? The time constant sets how much noise I'm going to have left over in my output. And there's a neat way of thinking about this, which is that the time constant kind of sets a window around which I accept signals around this frequency right here. And there's a delta f right here. And roughly speaking, the delta f, just by dimensions, is equal to 1 over tau. So this is another way of looking at the question of how long should I set my time constant. If I set my time constant to 1 second, say, then roughly speaking, I'm going to have a bandwidth in here of about a hertz, inside of which, if I have interference lines or anything like that, they're going to mess with my, my lock-in output. But if I have an interference line that's way out here that's 10 hertz away, it's going to be filtered out by the lock-in, and it's just not even going to show up in my lock-in output. But this noise acceptance rate here, around this bandwidth here, around the frequency that I'm actually locking into, the longer I set my time constant, the more narrow that acceptance window becomes, and the less noise I have inside that acceptance window. So therefore, the lower noise my output is. Okay, so I think that's all you need to know to get going on the lock-ins. You should look for a few things. Okay, as you get going, you should look at how do you hook up a reference. The reference signal that you put into the lock-in can be a square wave, it can be a sine wave, it can be a pulse, but there are limits on the amplitude of this. It can't be too small. If you have a 100 microvolt signal that you're trying to measure with your lock-in, you can't send the same 100 microvolt signal in and expect it to be the reference as well. That's too small. There are specs that you can look up in the manual and how big the amplitude needs to be. And also, if it's a pulse like this, say, what the duty cycle of the pulses are, what's the minimum pulse time, all that kind of thing. If you're going to use anything other than a sine wave or a square wave of reasonable size, say, a volt or something like that, if you're going to do anything other than that, consult your lock-in manual as to what the signal requirements are for the reference phase. Okay. Then you're going to take your signal and you're going to put it in. There usually are 2 inputs on a lock-in, A and B, and they are on coax inputs. Okay, B is the center conductor on the coax input. A is the center conductor on the A coax input. The outer shells are grounded typically, and often you'll just be wanting to do one wire, so you'll click a switch that just says pay only attention to this. Sometimes you'll want to use 2 wires, and you can lock into the signal that's contained on A minus B. That's just a detail to know about to let you know that the signal has to be there, or the switch has to be set to the right thing. On the signal area, you'll find the sensitivity setting. You just need to set that so it's reasonable for the signal that you're sending in. So it's such that you're not overloaded when the overlight light comes on, but preferably such that it's close to the signal amplitude, so you're using the dynamic range of the lock-in well. In other words, the signal's not so small, not microvolts at the point where it's doing the multiplier. And then finally, you're going to set the tau. Well, not finally. You're going to set the tau such that tau is long, right, compared to the period. So I'll write that as long compared to 1 over the frequency that you're chopping at, right? So if you have a kilohertz signal, the period's a millisecond, and you want to make tau long compared to that, but hopefully short compared to the time that you can stand to wait for the output to change. And then finally, you're going to set the phase. the reference phase. You're going to phase up the reference with the signal. You're going to do that by first zeroing it, right? Zero the output, right? And then switch the phase by plus 90 or minus 90, whichever you prefer. That'll just send the output to either very negative or very positive. Okay. All right. With that, good luck and have fun with your lock-in lab.